Well, good morning. This is about 11:02, I believe it is, on Thursday, the last day of November, 30th of November, 2017. This is supposed to be linear algebra, and right now I'm the only one in the room. So hopefully at least one or two students will be showing up soon. I did want to do a couple of announcements, so I hope you'll be listening to this. If you come in, I'll go in and make them again, but just so you'll hear. Please do the student course evaluations. Please do those. They're really focusing on that right now. We need to have as many of these done as possible. So I need both of you to do student course evaluations, please. All right. After that, let me say this. Normally on Fridays I have office hours on the Birmingham campus from 7:45 to 11:45. However, tomorrow I do not. Okay, I have an infusion scheduled for tomorrow morning, and that usually lasts all day. So I'll be at the Kirkland Clinic probably before 7, and probably be there until 4-ish or so in the afternoon. So I will not be on either campus tomorrow. Okay. Now, next. Your research papers. I think I only have one of those in, so the other person needs to get his in. This is your last weekend that you get to work on it. You can work on it the following weekend, but you'll be losing points if you turn it in after that, because they're due by next Thursday, 1 week from today. I think I've returned your first test to both of you. I hope I've returned the second test to both of you, okay? And I can't recall, do you have the third test already, or is that the one that we'll be working on now? I think that's this one that we'll do now. I will have that ready for you next Thursday, okay? And hopefully it will be something short enough that you can get it done easily within a week. Now, technically, it will be due in the following Thursday after, 2 weeks from today. I'll give it to you 1 week from today. It will be due then. You can get it to me anytime you want to. I'll be here all week that following week. I will be on the Birmingham campus that Friday, but I believe grades have to be in by Monday, I believe, noon on Monday. So I need to have all your work in by the end of the week, finals week, not next week. I'll give you the test next Thursday and get it back to me sometime the following week. And try to get your paper in before next Thursday so I don't have to start taking points off for that, because after Thursday I will. Now, if I were to get the paper today, this is the last day you can get that one last bonus point. But if I get it after today, then it'll just be your score. If I get it after next Thursday, it will start losing points. So please don't let that happen. All right. I think that's all the announcements. Where did we leave off last time? I believe it was linear combinations of vectors. And it seems like we've done this over and over in so many different ways, but let's do it one more time. An important type of problem in linear algebra involves writing one vector x as a sum of scalar multiples of other vectors v1 through vn. That is, for scalars, numbers c1 through cn, that the vector that you're interested in, let me get my pen activated here, if it'll come up, there we go. The vector that you're trying to write as a linear combination of some, I'm going to go on and use the term that we haven't hit yet, basis vectors. A basis, a set of vectors that everything, they're linearly independent usually of each other. That would be C1, V1, plus C2, V2, plus C3, V3, plus ... all the way up to and including plus C, N, V, N. Okay, so let's say we have a group of vectors, and you're wanting to write your solution vector x as some linear combination of those. That's what we do in linear algebra a lot, okay? So this is what we're looking for then, okay? Vector x is called a linear combination of the vectors v1 through vn. Now, they're not saying this yet. I'm going to go and say it for them, okay? If you're in n space, you're going to need at least n vectors to form a set like that. Then any other vector in that n space you can write as a linear combination of those. Now, any n vectors won't necessarily work. If two of those vectors happen to coincide on top of each other, then that's one vector, you know. So you need to have a unique set of vectors, v1 through vn, and there's not just one. I mean, there can be many different basis sets, but you'll need a set that they're all linearly independent of each other. Then any other vector in that, and get into the next term, in that space will be a linear combination of those. Okay? We'll get there later, but that's where we're heading. So let's do example 6. I think I'll clear this slide so we'll have room to do it. All right? Here is your vector x. I like to use vector notation. He uses parentheses. -1, -2, -2. Now, just looking at that, you can tell that's in 3 space, R3. All right, here's vector u. Vector u is 0, 1, 4. Vector v is, and that's also in 3 space, -1, 1, 2. And vector w, also in 3 space, 3, 2, 3, 1, 2. Okay. They're all vectors in R3, obviously. Okay? Now it says, find scalars A, B, and C such that vector x is equal to AU plus BV plus CW. Find the numbers, the scalars A, B, and C such that that's true. Okay? Now, I'm going to do it the long and gory way that basically is almost guaranteed to work. Should always work. -1, -2, -2, that's vector x, is equal to A times u, which is 0, 1, 4, plus B times V, which is -1, 1, 2. I hope you're checking me and making sure I did write all those correctly. I think I did. Plus C times vector W, which is 3, 1, 2. Okay? Now, what does it mean to add vectors? You add them by components. Okay? So I'm going to rearrange this ever so slightly here and do 0 times A, that's just going to be 0, minus B plus 3C is equal to -1. The first vector, the first component here is 0, so A times 0 is 0, plus the first component here, that's a -1 times B, plus the first component here, plus 3 times C, is equal to the first component there, -1. Then do it for the next one. That would be A plus B plus C is equal to -2. The second component here. We did A times 1, or 1 times A is A, 1 plus 1 times B is B, plus 1 times C is C, is equal to -2, the second one. And then the third equation would be 4A plus 2B plus 2C is equal to -2. Okay? Now, guess what? That's a system of equations, three unknowns, and that should be solvable. Okay? In fact, it's solvable using techniques we already have done. Just to save on space, I'm going to go on and do the first step. I'm going to write the matrix, which is the coefficients. Okay? For the first one, we would lead with a 0 here. We don't like having a 0 there. We won't have a 1, so I'm really going to exchange these two equations, which is like swapping two rows. So the first one is going to be a 1, 1, 1, negative 2. Okay? Second one's going to be a 0, minus 1, 3, negative 1. Now on that third one, I see no reason in the world to have multiples in there when you can simplify it by just dividing by 2, and that would be a 2, 1, 1, minus 1. Okay? Now, I'm going to do my row reduction. We got a 1 here, that's why we swapped the first two rows so we could get a 1 there. That's nice. Have a 0 below it, that's nice. To get a 0 down here, we'll do negative 2, row 1, plus row, I tell you, I can't read my writing here. Okay. Negative 2, row 1, plus row 3. It's going to be the new row 3. So this becomes, we're using row 1, 1, 1, 1, negative 2. Not changing the second one, so 0, negative 1, 3, negative 1. And the third one is going to be a 0 because negative 2 times 1 is negative 2 plus 2 is 0. Negative 2 times 1 is negative 2 plus 1 is minus 1. And negative 2 times 1 is negative 2 plus 1 is negative 1 again. And negative 2 times negative 2 is plus 4. Minus 1 is 3. Okay. Now, we got a 1 there, 0's below it. We want a 1 there. That's pretty easy to do. We'll make that a plus, that a minus, and that a plus. Okay? We'll just multiply the second row by negative 1. Or divide by negative 1, it doesn't matter. Okay, now we got the second row. Now we want, and it depends on whether you want to do Gauss elimination and back substitution, or just go and do Gauss-Jordan elimination and see what your answers are. This one's going to work out pretty easily to do that, so let's do it. We're going to add, you got a 1 here, that's what you want. You need zeros above and below. So on the top, I wish I'd have thought to do this before I changed the second row. But minus row 2 plus row 1. Okay, that's going to make that a 0. And that'll give you minus 0, which is 0 plus 1 is 1. Minus 1 plus 1 is 0. 4 plus 1 is 5. 3 plus 1 is 4. And minus 3. Minus 1 minus 2 is minus 3. Okay? Second row we're fine with for now. 0, 1, negative 3, 1. And the third row we're going to add row 2 plus row 3. Get the new row 3. And that'll be 0, 0, negative 4, 4. Okay? Sorry. All right. Now it's not so pretty anymore. Oh, yes it is. It's not bad. What, we got a 1 here, 0's below it, 1 here, 0 above and below. We got a negative 4 there. We want it to be a 1. Well, let's divide the third row, R3 divided by negative 4. Yuck. Okay. Okay, R3 divided by negative 4, and that will become, okay, I'll do it. 1, 0, 4, negative 3, 0, 1, negative 3, 1, and 0, 0, 1, because you're dividing by negative 4, negative 1, because you're dividing 4 by negative 1, by negative 4. So that's a negative 1. All right, now what we got to do is minus 4, row 3, plus row 1. You got 1s here, 0 below it, 1 here, 0 above it, below it, got 1 there. We want zeros above it, so to get that 4 to be a 0 is negative 4 times 1, and add that to row 1, okay? So that becomes, third row we're leaving alone, 0, 0, 1, minus 1. And by the way, we know right now C is equal to negative 1, okay? We can tell that by that last row. Okay, so row 1. Negative 4 times 0 is 0, plus 1 is 1. Good for that. Negative 4 times 0 is 0, plus 0 is 0. And negative 4 times 1 is negative 4, plus 4 is 0. That's exactly what we wanted. And now negative 4 times negative 1 is positive 4, minus 3 is 1. Okay? Get the second row, to get that 3 to become a 0, we 3 times row 3 plus row 2. Okay? So let's do that. 3 times 0 is 0, plus 0 is 0. 3 times 0 is 0, plus 1 is 1. 3 times 1 is 3, minus 1 is 0. And now the one we've been looking for, 3 times minus 1 is negative 3 plus 1 is minus 2. Okay, so this tells us that A is equal to 1, B is equal to minus 2, and C is equal to negative 1. So that says if we plug those in here, this would be 0, 1, 4, minus 2 times that would be plus a 2 okay, hold on just a minute. Eyes are going a little crazy on me. Negative 2, okay, yeah. The B is a negative 2, and I'm multiplying that by a minus 1, so that makes it a plus 2. And B is a negative 2 times that would be, pretty sure that's going to be a minus 2. Yeah, okay. And then a minus 2 times 2 is going to be a minus 4. I hope I'm doing that right. Okay. And then a minus 1 times C would be a plus a minus 3, minus 1, minus 2. Okay, we just negate everything there. Well, let's see what we got if we do that. You get a 0, 2, minus 3, that would be a minus 1. Got it? A 1 and a negative 2 would be a minus 1 is minus 2. Got it? 4 minus 4 is 0, minus 2. Got it. Yep, that gave us an x. So, for those three vectors, whether they're basis vectors or not, u, v, and w, in R3, you can write x as a linear combination of those three vectors. So, we've just done it. You find your A, B, and C, and you can do it by row reduction or however you want to. Okay? Now, and they got the same thing we did. X is equal to 1 times u minus 2 times v minus 1 times w. Got it. Now, sorry. There's a little discovery over on the left-hand margin. Let's just take a quick look at it. Is the vector 1, 1 a linear combination of the vectors 1, 2, and -2, -4? Okay? Now, after you've done this a while, you'll be able to look at that and say, absolutely not, because 1, 2, if you multiply that vector there by -2, you get -2, 4. So those two vectors lie on the same line, so there's no way you can get vector not on that line to be a combination of those two that are on the same line. Similarly, determine whether the vector 1, 1 is a linear combination of the vectors 1, 2, and 2, 1. And again, I don't believe, well, wait. Yeah, you should be able to do that one, I think. Same way we just did. Let's do that. All right. Okay. Is 1, 1 a linear combination of A times 1, 2 plus B times 2, 1? Okay? Well, this is saying that A plus 2B is equal to 1, and 2A plus B is equal to what? Okay? Well, that's a pretty simple one to do. Let's multiply the top equation by -2 and add it to the second equation, and that would give you -2a plus 2a is 0, so that goes away. -4b plus b is -3b. Sorry, my stomach is growling. I grabbed a cookie right before class because I was hungry in the middle of my last class, and it wasn't enough to stomach that. That was just a tease. Okay, so that's a -3b is equal to -3. 2 plus 1 is -1, so b is equal to 1/3. And then if you plug that in either one of those, you have 2a plus 1/3 is equal to 1. So 2a is equal to, subtract 1/3 from both sides, and so a is equal to 1/3 also. Is that right? So let's see. 1/3 2/3 plus 2/3 1/3 is 1, 1. Sure enough, that is. Absolutely. All right. What is the geometric significance of questions 1 and 2? Question 1 basically says you can't create a vector out of two vectors that are along, not on the same line, but with the one you're looking for, but they are on the same line with each other. There's no way you can form a linear combination of two parallel vectors to get one that's not parallel. And the second one is if you have two vectors that are not collinear, well, is every vector in R2 a linear combination of the vectors 1, 2, and 2, 1? I would say yes, because it's two-dimensional space. You have two vectors that are linearly independent of each other. They form, and later we'll call that a basis, and therefore any other vector could be created from the adding those two vectors together. Okay. Now, bottom of the page here. Sorry, I keep clogging up a little bit. You often find it useful to represent a vector u as u1, u2, u3 up to un in Rn as either a 1 by n row vector, row matrix or a row vector, or an n by 1 column matrix or column vector. This approach is valid because the matrix operations of addition, scalar multiplication give the same results as corresponding vector operations. That is, the matrix sums and whether you write those as columns or rows, they're going to give you exactly the same thing. Yield the same result as vector addition so I guess that's a technique to make some of your calculations that are going to be coming up a little bit easier. Okay. Homework exercises 4.1. I may have to go get some water in just a second. Do number 1. Either 3 or 5 or both. Either 7 or 9 or both. I've assigned some of these before. Either any of the odds 11 through 15. Do 17. Do any of the odds 19 to 23. Okay. Just looking at those and trying to. Okay. Do either 25 or 27 or both. Do 29. Do 31. Do either 33 or 35 or both. Do 37. Do any of the odds 39 to 43. And then what we were just doing, either 45 or 47 or both. More of that, 49, 51, 53, and then you can do 55 if you'd like, and then 57 and or 59 if you'd like. 61 is another proof. No, actually either 61 or 63 are proofs of some of the properties we were using. 65 is not a bad one to consider. Okay, that gets us to 4.2, which is the title of it is Vector Spaces, which is also the title of the chapter. So let me clear this out of the way, and since this is a decent stopping point, I hate to do this, but I'm going to go clear my head out and get something to drink because my throat is getting pretty raspy feeling. So I'm going to put this on pause. All right, I'm back. I think what's happening, it's raining outside and it's cooled off outside, and I think then it's cooled off some in here, and that's probably why my head is clogging up on me. And I'm not going to say I'm a lot better than before, but at least I got something, cleared my head and got something to drink. So hopefully I won't be as gravelly in the voice, but we'll see. So 4.2, which is the title of the chapter 2, Vector Spaces. I'm going to start with the definition. Now, I've already been sort of hinting at it as we've come, but back in the last section, Theorem 4.2 listed, I'm sorry, yeah. Back on page 150, Theorem 4.2 lists 10 special properties of vector addition, scalar multiplication. We did those last time. Suitable definitions of addition and scalar multiplication reveal that many other mathematical quantities, such as matrices, polynomials, functions, lots of things share those 10 properties. So, the point being, any set that satisfies those properties, and sometimes they're called axioms, is called a vector space. Okay, and the objects of the space are called vectors. Whether they're a vector in the classic sense that we've been using before, like a vector we say is in 3 space would have 3 components, x1, x2, x3, or something like that, x, y, z. It doesn't have to be a vector, which is a directed line segment. It could be a matrix. It could be a polynomial. It could be a function. They don't have to be the classic vectors that we've talked about before to be called the vector space and the objects to be called vectors. It is important to realize that the following definition of a vector space is precisely that, a definition. You do not need to prove anything because you're simply listing the axioms required of vector spaces. This type of definition is called an abstraction because you're abstracting a collection of properties from a particular setting, that is Rn, or Pn if it's polynomial space, what were some of the others, matrix Mn if it's a matrix space, or Fn if it's a function space. But they're all vector spaces, okay, to form the axioms for a more general setting. So here is the formal definition of a vector space, and if it looks and sounds pretty common to what we've had before, it's because it is. We've been leading up to this. Now we're going to call a vector space by name, and we're going to use capital V, okay? It's just like the function we quite often call it f of x. Vector spaces we quite often call capital V, okay? Now, if you have more than one, you'll use V and W or something like that, or V and U or something. You can name it anything, but usually capital V or a capital letter is a set, okay? Let V be a set on which 2 operations okay, and these 2 operations are vector addition and scalar multiplication. Okay, those 2 operations are defined. Okay. It's a space, it's a set on which those 2 operations are defined. If the listed axioms are satisfied for every u, v, and w in that space, if these 10 axia, okay, they call them axioms, which I don't really think is the proper plural for it, but that's all right, are listed for every, if these listed 10 axioms are satisfied for every u, v, and w in V, in that vector space V, and every scalar C and D, I think they call them. Yeah, C and D. You can name them anything, but I'm trying to use the same as book. Then, if all that's met, then V is a vector space. Okay. Here are the 10 axioms. Okay. U plus V is in V. Okay. So in other words, if you have vectors in this vector space, U and V are both in the vector space, you add them together, you can't suddenly be out of the vector space. You have to also be within that vector space. Okay? We'll see some examples, and that's, by the way, is called closure under addition. Okay? Second, these, you've seen them before. Anytime you add two vectors within that vector space, u plus v, you'll get the same result as if you had added v plus u. So the order doesn't matter. This is a commutative property of addition in that vector space. Okay? They just say commutative property, but there's used to be a commutative property of multiplication. It will not be on this, but that's why I like to say of addition. Okay? Number 3, if you start with the vector u and add it to the sum of v plus w, you'll get the same results as if you had started with u added to v and then add that sum to w. It doesn't matter. You'll get the same answer, and this is the associative property of addition. They just say associative property. It's of addition. In many things, multiplication has associative properties, not with vectors. Okay? Number 4. V has a zero vector such that for every u in v, u plus 0 is u. V has a zero vector. Okay? Such that for every u in v, u plus that zero vector is simply always u. Okay? That's the additive identity. Okay. Number 5. Just as before, for every u in v, okay, there is a vector in v, and this vector will be minus u, such that u plus minus u is equal to the zero vector. Has to happen. That's the additive inverse. Okay. Number 6. I'm not going to have room for them all. Those are the 5 that deal with vector addition. The 5 that deal with scalar multiplication is that any constant c times any vector u in that space will be also in that space. Okay? I use that symbol, an element of. Okay? That is also an element in the vector space. Okay? And that's the closure under scalar multiplication. All right. Now, and they actually use those words here, closure under scalar multiplication. I was afraid they'd just say closure in multiplication. Okay? It's scalar multiplication. I'm glad they use that term. All right, I need some places to write the other 4. I'll try to get it up here. Number 7. C times u plus v. You can distribute the c across the parentheses, and that'll be cu plus cv. Okay? That's distributive property, and that's all they say. I like to say distributive property of scalar multiplication over addition. Okay. Number 8. This time you have two scalars, c plus d, multiplied by one vector, u, and that would be cu plus du. Okay? And that's... Hey, good to see you. I'm sick and tired of talking to myself. Okay.
How was your Thanksgiving?
It was very good, thank you. How about yours?
It was pretty good.
All right, good. Let me go through a couple of announcements I made early since you're here now. You may not go back and listen to, I encourage you to, but in case you don't, I want to make sure you hear the announcements. Flip my lights. So I'm going to project to come up anyway. Okay. First, and I think foremost, you weren't here last time and I said it this time, so I'm going to say it again. Have you done the student course evaluations yet?
Not yet.
Not yet. Okay, you know how to do them?
Do I know how to do them?
Yeah.
Look at like emails, right?
Yeah, if you go to your email, you'll find one that has the link in it and everything. That's the easiest way to do it. If you didn't do that, I have a few students say, oh, I don't know how to do my email. You know, they should, but they don't. Then you have to go to the website and do quick links and then look for the evaluation thing, and then when you find that, then you're there. So much easier to go to the email and click on the link. All right, please do those. I have actually heard some pretty high administration people say, don't give the final until the evaluations have been done.
That don't make no sense.
I don't think it's good to force students to do something. I don't think you get a good evaluation then. I mean, not good or bad. I don't think you really get their opinion right if you're forcing them to do something. So I'd rather have an honest opinion. Okay. But number two, some students may want to wait to see what the final grade is before they do the evaluation. Okay. I want them to have that right. Okay. But then you can't hold off the final exam until you can't do it that way.
Okay.
So I highly urge, because I remember when I was an undergraduate, I know it was a long, long time ago, but once that end of the term came and I took that last final exam, I was so anxious to get out of there, I would have forgotten to go back and do an evaluation. So if you're anything like me, don't wait too long. Okay, go on and do it. You already have a pretty good idea of what your evaluation is, of course.
Yeah.
You're not waiting on one piece of information, so go on and get it done. Okay? Number two. Most Fridays I'm on the Birmingham campus, 7:45 to 11:45, office hours. Not tomorrow. I've got an infusion tomorrow. I'm going to be at the Kirkland Clinic probably before 7 o'clock in the morning. Probably won't leave until somewhere around 4-ish or so. So not go. Yeah, it's all day long type thing. They have to do it really slowly because it's a monoclonal antibody, and it's developed, I think, in rats. Okay, and they try to strip all the rat stuff out of it, but you still will get traces of it, and you can have a reaction to it. And in fact, just about every time I break out in a little rash. It's nothing bad. I just pop another Benadryl and I'm okay after 10 or 15 minutes. But they can't give it to you fast because people could go into anaphylactic shock and they could actually lose consciousness. And they don't want that happening. So they do it very slowly. They give me 2 Tylenol to take before they ever get started. Once they get the drip going, the IV going, they give me 2 different steroids to cut down on that, and then they give me Benadryl, usually through the IV, and to cut down on the things. But it's usually about midway through, because it lasts most of the day. Usually about midway through, the Benadryl's run off or worn off, and I start breaking out. So I just pop another Benadryl, and usually within 10 or 15 minutes, I'm fine. So it is a slow process, and the Benadryl knocks me out. So I try to sleep through most of it, but once I get that itchy breakout, you know, I can't sleep then, so that's when I pop the other Benadryl. So I usually grade papers and stuff like that up until the Benadryl kicks in. It's worthless. Okay. So anyway, it'll take most of the day. All right. Next thing. Research paper. Okay. This is your last weekend to work it. You don't have to work it on weekends, but I just figured that's your biggest chunk of time. This is the last weekend before it's due. It's due by next Thursday. If you can get it to me sooner, great. If you can get it to me today, you get that last bonus point. Okay? But today's the last day to get that bonus point.
Yeah, I do remember you saying something about that.
Yeah.
That's on Blackboard, then?
Yeah, it's on, under content, under Blackboard.
Okay.
You'll see those things, and if you go to the video, the YouTube video that I did on that, you can hear me talk about it. So it's out there in two places. Static, under research paper general instructions, or dynamically, that first or second day of class, I go over it in gory detail. Okay. So that's, yeah, you can find out all the stuff there. If you are on campus tomorrow and bring it by, just slide it under my door. I won't be here. But do it on this campus. Don't go to the Birmingham campus. Not that door. 265 is my office door. Yeah. But if you do it next week, that's fine too. But earlier in the week, the better, because I can get them graded before I start getting finals coming in. So, but I will accept it up until Thursday. But after Thursday, you start losing points. So please get it to me before Thursday.
Okay.
Sooner the better, though. I think I've returned both the other tests to you, haven't I?
Test 1 and test 2?
Yeah.
I believe. I saw my grade on Blackboard.
Okay, I know you, I put the grades out there.
Yeah.
Let me see. There's test 1. I know I returned test 1 to you. Both of you. Nope, I didn't return test 2. I thought I had. Sorry about that.
That's all right.
And Jasmine, I got yours too if you're listening. I've given you test 3, right? The one on determinants?
Yes, sir.
Okay, good.
Yeah,
Okay.
I turned in. Yeah.
Okay, good. I thought there was a third test.
Yeah.
And then, so next week I'll give you the fourth test. Okay. Okay. I thought we had one more chapter in there. All right. So I'll pass those out to you on Thursday. I'll give you the last test. So we'll be just covering what we cover in chapter 4.
Okay.
So, all right, good deal. All right, so I was going through 4.2 is vector spaces, okay, which is the title of the whole chapter, too, is vector spaces. And this is the definition for a vector space. And they usually give them a title like a capital V or something like that. So if V is a set in which the two operations, vector addition and scalar multiplication, are defined. If these 10 axioms, the book calls them, are all satisfied for every u, v, and w in that vector space, and for every scalar c and d, then this is indeed a vector space. Okay, so it starts off being just a set under which those operations are defined. All 10 of these axia are met in that definition, then V is also a vector space. Okay? And I went through the first 5. These are the addition ones. And starting with 6, 7, and 8, these are the multiplication ones. And that's where we were right when you came in. So let me complete that. If you sum the two scalars, multiply by a vector, that's going to be C times U plus D times U. That's also a distributive property, but this is a distributive property of a vector multiplication over scalar addition. Okay? The first one, the previous one, was scalar multiplication over vector addition. This is vector multiplication over scalar addition. Okay? They're both distributive properties, but I think you need a little more to distinguish. Okay? Number 9. This is C times du. If you have scalar C times the vector formed from scalar D times vector U, then that's the same as CD times U. And they put these in parentheses times U. Okay? So in other words, it's sort of an associative property, but it's an associative property of multiplication of two scalars and one vector. We haven't even defined what we mean by multiplying two vectors together in this sense yet. Okay? And if we did, I'm not sure they would associate the same way. So this is just one associative property. Okay? And then the last one, number 10, is the scalar 1 times the vector u is going to be the vector u. Pretty obvious, and that's scalar identity. In other words, 1 is the identity element, just like it is in real numbers. So those are our 10 axioms that if all of them are met, and frankly, I cannot ever imagine a set of anything where number 10 won't be met. Okay, I mean, it's pretty obvious. The others, they may not be. Okay? It is important to realize that a vector space consists of 4 entities. 4 entities. A set of vectors. Now, in this section and for the rest of this section, this chapter, remember a vector is not just 4 components, or 3 components, or 2 components, or 17 components. Not a directed line segment like we've been a vector before. A vector in this sense can be a polynomial, it can be a function, it can be a matrix, or it can be a regular vector. There's lots of things that could be vectors that we don't usually think about vectors. So it's important to realize that a vector space consists of 4 entities, a set of vectors. They may be polynomials or functions or other things. A set of scalars, those are just numbers. Those are always just numbers. And 2 operations. Vector addition, scalar multiplication. That's it. Okay. So it says 4 entities, set of vectors, set of scalars, and then vector addition and scalar multiplication. Those 2 operations. When you refer to a vector space V, be sure that all 4 entities are clearly stated or understood. Unless stated otherwise, assume that the set of scalars is the set of real numbers. Unless, for some reason, those scalars come from somewhere else. The first 2 examples of a vector space should not be surprising. They are, in fact, all models for use in the 10 vector space axioms or axia. R2 with the standard operation is a vector space. We've already talked about it, so let's do example 1. Okay. What we're showing is the set of all ordered pairs with real numbers, R2 with the standard operation is a vector space. So here's our set of all ordered pairs okay, of real numbers that's R2, real numbers, 2 dimensions of R2, with the standard operations, and that's exactly like we've defined them before, is a vector space. Basically, we're talking about 2-dimensional vectors. That's a vector space.
What section is it?
What's that?
What section?
What section?
Yes, sir.
This is Chapter 4, Section 4.2. Okay? Example 1, bottom of page 155. Now, it says to verify this, look back at Theorem 4.1, which is basically those 10 axia that we just looked at, and all 4 of them work. Okay? Now, vectors in the space have this form. V is 2 space, so this is ordered pairs. So this will be V1, V2. Now, this is another thing that sort of drives me a little wacko here. Excuse me. They call that an ordered pair, and it is, set of all ordered pairs. Now, when you write that, though, you might think they're talking about directed line segments, vectors. These are just ordered pairs. They don't have to be vectors, okay, in the old sense of the word, but they're saying now, since it's a vector space, they are vectors. So those are really parentheses. Those are ordered pairs, not vector symbols indicating vectors. But it's almost a moot point, distinction there. Okay, you go back and look at the 10, they're all there. Okay, so that's all they do for example 1. They point you back to 4.1, which was on page 148, 4.1, those 10 properties are exactly your 10 axia. Exactly. So since they fit that, that is a vector space. That's all they do for that. Okay? Example 2. I think I'll go on and erase this one, but it's going to be almost that simple again. I hit the wrong key. Okay? Example 2. Oh, no, I'm sorry. Rn is a standard operations with standard operations of vector space. The set of all ordered in tuples. Okay, of real numbers Rn, that's what it stands for, that's the symbol for it, with standard operations is also a vector space. Is a vector space. Okay? And what you do for that, just turn back to 4.2, which we just did last time on page 150. And that was for Rn. You see those 10 properties there are exactly your 10 axia that we have on page 155. Nothing new there. So therefore, these are vectors, is a vector space as well. Okay? Now, this is one a little bit different. Okay? And this one, example 3, vector space of all 2x3 matrices. Okay? Show that all of the set of all 2x3 matrices with the operations of matrix addition and scalar multiplication is a vector space. Okay. Now, we'll assume the A, and that will be A11, A12, A13, A21, A22, A23. That certainly is a 2 by 3 matrix, right? Okay. And some other matrix B, B11, B12, B13, B21, B22, B23. That's a matrix in a 2 by 3 matrix. Any two of those, because it says all these matrices, 2 by 3 matrices, these represent any one of those. Okay? Now, what you do is start thinking. Okay? And if you got those 10 axia down, I don't know if you copied them or not, but the first one was, if you add those two together, or any two together, you're also going to get a 2 by 3 matrix, right? Because it'll be A11 plus B11, that'll be the first entry. A12 plus B12, that'll be the second entry. A13 plus B3. Okay. You'll wind up with 6 entries in exactly that form. That's also in the vector space. So it's closed under matrix addition. Okay? And if you add these two together, A11 plus B11, A12 plus B1, or you do them in the reverse order, B11 plus A11, that's the same thing. Those are just real numbers. Doesn't matter which order you do, so they commute. No problem there. Okay? 3. Okay? Actually, you have to come up with a third one. I don't know why there's just a 2 here. You can go back to theorems 2.1 and 2.2, way back in section 2.1 or 2.2, and you see all those other things fit. Now they're not doing them all. I sort of wish they had just to begin with. They would have needed a third matrix C, C11, C22, C12, C13, C21, all like this. And then if you had added those together, added the first two, or the first one grouped with the other two, add them together, they commute. I mean, they are associated. So that fits. Okay? Now, this does have a zero vector, because these can represent any vector in the world. The zero matrix would be 0, 0, 0, 0, 0, 0. And that matrix, if you add it to any other matrix, like A, you'll get A11, A1, you'll get A again. Add that zero matrix to B, you get B again. Well, that's the zero identity, the additive identity element. And you could also do the negation of this. If you do minus A11, minus A12, minus A13, minus A21, add that to A, you get 0, 0, 0, 0, 0, 0. So yeah, that's the additive inverse. Okay? So all the additions work. The scalar multiplications work. Any scalar C that you add to by either one of those, you're going to get a matrix in 2-3 space, right? It'll just be CA11, CA22, CA313. Yeah, you'll have all those in there. It's still in the space. So it's closed under matrix multiplication. And then if you added those two together and multiplied by a matrix, you get the same as multiplying the matrix by first plus the matrix by the second. It works fine. Every one of those works. 1 times any one of those matrices is the same matrix. So yes, every one of those axia work for that. Now here's what they do. They typically shorten it. And here's how they shorten it. If A and B are 2 by 3 matrices, C is the scalar, then A plus B, the addition of two matrices, and CA are also 2 by 3 matrices. That's the closure thing. So therefore they're closed under matrix addition, scalar multiplication, and then you can plug in the others and they all work. Now one to watch for, you might have made sure you do have a zero matrix, zero vector. Every one of these. If you don't, it's not going to be a vector space. Maybe a set of matrices or a set of vectors or other things, but it won't be a vector space. Okay? I was going to see if we could get number 4 done, but I don't think we're going to have time. So we're going to pick up there next time. Example 4. Okay? Now, homework exercises here. We didn't really get too far along. I think you can do any of the odds 1 through 5. Well, maybe not. I know you can do 3. You can do 1 and you can do 3. Okay? Describing the additive inverse, you can do 7 or 9. Okay? You can probably do some of the others, but we just haven't done one like that. Okay. We'll hold off on the rest of them and do those later. Okay. Good deal. Any questions? All right. So I'm pretty sure we're going to finish 4.2, and I believe we'll get into 4.3. That's not going to take too long, I don't think. Hopefully we'll get into 4.4. And if we can get to 4.4, that's probably all your test will cover. We may not finish 4.4 because it's a little bit long, but we'll try to get there. I wish we had time to get to 4.5, but I doubt if we're going to make it this time. So we'll get as far as we can and go from there. Try to get the papers done, do the student course evaluation.